Okay, our last video on electrostatics, we are going to start by talking about what an electroscope is, and then we'll talk about electrostatic force. And that'll actually cover everything you need to know in the field of electrostatics before we move on to circuits. An electroscope is a really neat tool, and I have a bunch in the classroom that we will use, and we will get to play around with them, and you'll see how exactly they work. What it is it's an object that is used to determine the type of charge on another object. I'm going to start off by drawing a picture of the electroscopes that we have here in class. So what this is a glass casing. Protruding up out of the glass casing is this metal knobby looking sort of thing. Looks like that, and then it's connected by a strip of metal down in through the glass casing. There are two hooks on the end. So the glass casing is essentially to isolate the what hangs from these hooks, because what hangs from these hooks are gold leaf, just kind of leaves. So they're made out of, they're metallic, but it's gold leaf, so it's very, very thin. Okay, so we have a metal knob up here, and we have leaves. Those are these kind of straight lines hanging down. And right now the leaves are kind of just hanging straight down. In other situations, these leaves actually move up and kind of stick out to the side. So they kind of stick out like this, okay? Now, I'll get to how that happens in just a second. An electroscope can be charged by one of two methods. Can be charged either through conduction or induction. And what I was just saying about the leaves sometimes separate and kind of spread apart from one another, that happens whenever the electroscope becomes polarized or is charged. Causes leaves to spread apart. Now let's explain a little bit about why that happens. If the electroscope is neutral, then the leaves hang down like this. If you were to polarize the electroscope, remember polarize means to separate the charges into kind of two sections. It doesn't mean to charge it, so the electroscope is still neutral during polarization, but we've just separated where the charges are. Like for instance, let's say we bring a negative charged object near the metal knob. Well, that negatively charged object is going to force the electrons that are spread throughout the electroscope as far away from the negative object as possible. If the negative object is up here, that means they're going to spread down into the leaves. If both of these leaves become negatively charged, then they will want to repel each other. So the leaves kind of go like this. I'm going to draw a dotted line so you see what they might look like. Okay, the leaves might go like that. Same thing if it's a positively charged object. If it's a positively charged object in a neutral electroscope, then what that's going to do is it's going to pull electrons up through the electroscope towards this metal knob. What that's going to do is leave the leaves with a lack of electrons, with a lack of negative charge. They'll then be positively charged, and they will separate. There's no such thing as having one leaf be positive and one leaf be negative. That doesn't happen, okay? This is all one connected object because they're all parts are touching. Sometimes you'll see an error where the leaves kind of just snap together and they looks like they're stuck together. That's just a mistake. That's not supposed to happen. That's some sort of static effect that we don't actually want to happen. So that's what happens if the electroscope is polarized. If we put a charge on it, let's say if we put a net negative charge, then that means that the electrons will have, essentially there's going to be a surplus of electrons throughout the electroscope, which means there's a surplus of electrons on the leaves, which means they'll spread out. If the electroscope is positively charged, then what that means is that there's a lack of electrons, which means there's got to be a lack of electrons in the leaves, and again, the leaves will spread apart. So all in all, when the leaves are spread apart, that indicates the charge, that the electroscope is charged, or at the very least polarized. The key to determining it is polarization means that if you take the object that's doing the polarizing away, the leaves will collapse back to normal. If the electroscope is in fact charged, then the leaves will stay out even when no charged object is near it. So that's how you can tell the difference. So the electroscope is neat, and it's kind of useful because if you know the type of charge originally on it, you can determine the charge of other objects by examining what happens to the leaves when brought close. When object comes near. Here's what we mean by that. Let's look at the example. Let's say that the electroscope originally has a negative charge on it. So it's negatively charged, which means the leaves are separated. What happens to the leaves if a positive object is brought close? Let's think about this for a second. If a positively charged object is brought close to this negatively charged electroscope, then that means that the positive object is going to attract the electrons in this object. There's a surplus of electrons in the electroscope. They're going to want to go near the positively charged object. If you bring the positively charged object near the metal knob, that means the electrons are going to congregate in the metal knob. And since electrons can move throughout the electroscope, that means that electrons from throughout the electroscope are going to go towards the metal knob. Some of those electrons were bound to have been in the leaves, in the gold foil leaves, making them spread apart in the first place. If not as many electrons, because not all of them are going to leave, but if not as many electrons are now in the leaves, they're not going to repel as strongly, so the leaves will actually move closer together. The leaves will collapse. Now, what if we bring a negatively charged object close to it? What's going to happen then? Okay, so if the electroscope is negatively charged, we bring a positively charged object near it, the leaves collapse. What if instead we bring a negatively charged object near the electroscope? That's going to have the reverse effect. There's a surplus of electrons on the electroscope. The negatively charged object getting brought near the metal knob will repel electrons from the metal knob. They'll go down as far as they can to get away from it. Again, the function of the glass casing is to make sure that that electric charge can't leak out or escape. If the electrons are fleeing from the metal knob, they have no choice but to go into the leaves. If the leaves are already separated because there's negative charge there, if you put even more negative charge onto the leaves, they should separate even more. So if a negative object is brought close to a negative electroscope, then the leaves separate more. So that enables us to tell if we have this charged object and we're not sure what type of charge is on it. Now with the electroscope we can tell what type of charge is on that object, but we do have to know the original charge on the electroscope. Okay, so we're going to look again at electroscopes in class, maybe do some demos with them in person, maybe look at some simulations. What I want to move on to now is the electrostatic force. The electrostatic force you did last year, it's fairly straightforward. It is the force between two electric charges. Okay, and the equation for the electrostatic force, as you remember from last year, is Fe, electrostatic force, equals K Q1 times Q2 over R squared. So now let's talk about what all these different symbols mean. Fe is obviously the electrostatic force. K is not the spring constant. Please don't get that mixed up. This is a different K. It looks the same, but it means something different in this context. You need to know the context. K is the electrostatic constant. Last year, I believe you were told that the electrostatic constant had a value of like 8.99 times 10 to the 9th. This year, we're going to round that right up to 9 times 10 to the 9th, and the units of that are newtons times meters squared over coulombs squared. Okay? So that's just a constant. We discovered that constant through doing experiments. I do want to point one thing out. Sometimes on the in multiple choice answers, and I believe it might even be on the reference sheet, although I'm not sure, they state the electrostatic constant in a slightly different way. Sometimes they state that it is, or you might see this sort of a similar sort of thing in answers. 1 over 4 pi, and then this kind of slanted e with a naught. That's called an epsilon naught. That is, and whenever you see that, it's just referring to the electrostatic constant. These two are equal, okay? Epsilon naught has a value. It might be on the reference sheet. I don't have it in front of me, but if you ever see this epsilon naught, what all it is just showing you, again, all it is just showing you a, it's a different way of writing the electrostatic constant, okay? It's a constant that you might be able to even look up on the reference sheet, but that's what it's in reference to. Okay, so there's K. We know that Q1 and Q2 are charges. And we know that R is the distance between centers of charge. So in other words, how far apart are these charges? We're going to do one example, and we kind of actually did it last year, but we're going to do one example right now of what the, to just demonstrate how the general magnitude of the electrostatic force versus something else that's kind of similar. In a hydrogen atom, where the electron and the proton are 5.2 times 10 to the negative 11th meters away from each other, we want to determine the electrostatic force and the gravitational force between the two particles. Let's do the electrostatic force first. Fe equals K Q1 Q2 over R squared. We're dealing with an electron and a proton, so we know that the charges on those are 1.6 times 10 to the negative 19th coulombs, and we need to use coulombs because K, the constant, is given to us in coulombs. So 9 times 10 to the 9th newtons times meters squared over coulombs squared. We're not going to plug in a positive or negative because we're just looking for the magnitude of this force. So we have 1.6 times 10 to the negative 19th coulombs, 1.6 times 10 to the negative 19th coulombs, and the distance apart is 5.2 times 10 to the negative 11th meters. And again, don't forget, we need to square that because that's part of the equation. We type that into a calculator, 9e to the 9th times 1.6 e to the negative 19 times 1.6 e to the negative 19 divided by 5.2 e to the negative 11th, and because it's squared, I'm going to divide by that again. And what we get, I'm going to do second and scientific to convert this to scientific notation. What we get is the electrostatic force between this electron and proton is 8.52 times 10 to the negative 8th newtons. Very small, but consider that we're talking about an electron and a proton. Very, very small objects, okay? They are a very small distance apart, but these objects are tiny. So, and all in all, that's not a terribly tiny force. Now let's look at the gravitational force between these two objects. You'll remember that the force of gravity equation, if we're not dealing with an object in Earth, is as follows. G little m big M for our two objects over R squared. I don't have the reference table in front of me or the equation sheet, like I said, but you can look up G, little m, and big M right on the equation sheet, because in this case, little m and big M are the mass of the electron and the proton. G, big G, is a universal gravitational constant of 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Little m, the mass of an electron, would be 9.11 times 10 to the negative 31st kilograms. You can use M1 and M2 if you don't want to use little m or big M. It doesn't really matter. And the mass of a proton is bigger, but still tiny, 1.67 times 10 to the negative 27 kilograms. And the same distance divides them. 5.2, or separates them. 5.2 times 10 to the negative 11th meters squared. Again, let's calculate. Just looking at the numbers, I feel like we have much smaller numbers that we're dealing with all across the top, so we should expect a smaller answer. Let's go back to floating point for a second. 6.67 e 10 to the negative 11th times 9.11 e to the negative 31st times 1.67 e to the negative 27th. We're going to divide that by 5.2 times 10 to the negative 11th twice. And we end up with an answer of 3.75 times 10 to the negative 47th. That's not a mistake, newtons. 10 to the negative 47th. Crazy. Okay? So, some analysis with this. In this situation, the force of gravity is almost 40, not 40 times smaller, 40 orders of magnitude. That essentially means it is like 1, let me see if I can get this right, 1 over 10 to the 40th times smaller than the electrostatic force. 40 orders of magnitude smaller than the electrostatic force. That is tiny. People often think that gravity holds things together, and that's true, but only if we're talking about truly massive objects. Massive objects are held together by gravity. Tiny objects are held together by the electrostatic force. We would say that the force of gravity in this case is negligible. So what we see is that for small objects, the force of gravity, or excuse me, the electrostatic force, and the force itself is just inherently stronger. Now, why is the Earth held together by gravity as opposed to by the electrostatic force? That's because the Earth, the different parts of Earth, they're essentially electrically neutral. There's usually not very big buildups of charge on objects when you consider large objects. Once you get the masses big enough, those objects can be held together by gravity. Small objects that don't have very much mass, the force of gravity doesn't really hold them together all that well, but smaller objects can have pretty significant charge attractions on them. Okay, so they can have pretty significant amounts of charge building up between them. So smaller objects are definitely held together by the electrostatic force. Okay? So that's the electroscope, that's electrostatic force, that's everything that I want to talk about in terms of electricity. The next set of videos that I will be making will be on the basics of circuits. I'll see you for those later.